I think it's clearance.
Sorry?
I think it's clearance because the availability has to do with the volume or the concentration available for action to the sites, and then volume of distribution that has to do with distribution. Pharmacokinetics is now everything from absorption to clearance and everything. So I would go with clearance.
Oh, Seraphine, you're doing number 119.
Oh,
Sorry.
sorry. 119.
Yeah. Yes, first. 119 first. So, okay, so chemical structure of a drug, it needs to be, it needs to conform to the receptor, right? It needs to have that size fit in for the receptor. And its intrinsic activity is also dependent on that. Remember, we discussed agonist and antagonist, and the metabolism also, the enzymes which metabolize it. So I think the excipients, which are the just like additives, colors, I don't think those have any effect on the chemical structure of a drug. That's what I think. So anyone who has something to add on that or to correct me if I'm wrong.
Yeah, I also think it's D.
Okay, thank you. I think Shina, you can go with that because no one else is talking. Complete removal of a drug from a specific volume of blood per unit time. So Seraphine had answered that as clearance. That's okay. Seraphine, can you please repeat the explanation again?
I was saying for pharmacokinetics is not specific to everything because it's everything from absorption, metabolism, distribution, everything. So we can't call that anything about removing the drug from the system. Then bioavailability has to do with the amount that is available at the site of action. And then volume of distribution. I don't know how to explain volume of distribution.
Volume of distribution, is it the one which enters the tissues? Like if it has a very high volume of distribution, that means the drug action is low. I'm not sure.
Yeah, you're right. If a drug has a high volume of distribution, then it's distributed to the tissues, or it has a high affinity to the tissue proteins. If it has a low volume of distribution, then it's in plasma, so high affinity to the plasma protein.
Okay. That's okay. So the half-life of a drug is the time required to eliminate 75%. No, half-life means 50% of drug elimination, right? B says it's influenced by the rate of metabolism. Yes. Decreases in patients with liver disease. It does decrease and then reduces when the drug absorption slows down. The half-life of a drug I think it depends on the chemical structure of a drug and I don't know. What do
I
you
think
guys
the
think?
half-life of a drug, in most cases when you have liver disease, you end up not metabolizing the drug well, so the half-life should increase, I think. And then also, when the absorption is slow, then it means the drug will also be excreted slowly, so the half-life will increase. So I would think the answer is B. It would be influenced by the rate of metabolism.
Yeah, because you said it does increase in liver disease because it's not been metabolized, right?
Yeah,
So yeah, we can go with B. The volume of a distribution of a drug depends on mostly plasma protein binding, yeah, as we had said, renal excretion, route of administration, and drug formulation. So someone had said the volume of distribution is when the drug binds to the plasma. Is it when it binds to the proteins and goes to the tissues?
Yeah, when it has a high volume of distribution means tissue proteins, then low volume of distribution means plasma proteins binding.
Sorry, when it's high, you said tissue proteins.
Yeah, like how digoxin is concentrated in the heart muscle, so it has a high volume of distribution.
Okay. So if that means that it depends on the plasma protein binding, whether so if you're talking about high, now you're talking about the tissue plasma and protein binding, and if it's low, you're talking about the plasma protein binding, right?
Yeah, yes.
Okay.
Yeah, it's also one property that can be used to see if a drug can be dialyzed. So because for dialysis, we usually remove drugs that are in the blood. So if a drug has a high volume of distribution, it can't be dialyzed. If it's more concentrated in the blood, then it can be dialyzed.
Okay, that makes it simple. Thank you. Which of the following routes of drug administration is associated with highest bioavailability? Oral, intravenous, sublingual, intramuscular. So it's IV, right? Since it's administered directly to the blood system. Can we go with IV, Emma?
Yeah, I think so.
Okay, Shrina, you can mark IV, intravenous B. The rate of absorption of a drug can be increased by reducing drug particle size, formulating as an oil suspension, injecting of adrenaline at the site of location, and topical administration. So reducing particle size means increasing the surface area to volume ratio, right? So that increases absorption. If it's formulated as an oil suspension, I don't know if it's going to be high lipid levels. For epinephrine, I think we had discussed the local anesthesics. We were saying that it's injected so that the local anesthetic can just act on that, like so that the concentration the drug is concentrated at that site. So that means injecting, and it will not increase the absorption. Actually, I think it will reduce, so that it's just at that point and not absorbed to the other parts. So what do you guys think? Oh, you're asking. My explanation was reducing the particle size of a drug will increase its surface area to volume ratio. So that means now the rate of absorption will be increased. I don't know if that makes sense. Next question, the trough. Okay, the trough in a plasma concentration curve of a drug is the upper limit of a drug's concentration in the blood, the peak plasma concentration following a single dose, steady state plasma levels, and the lowest level of a drug in the blood. I honestly have no idea. So someone is saying D in the chat box. Please explain.
Can you hear me?
Yes.
All right, let me just Shrina, just allow me to annotate your screen kiasi.
Wait, let me do the whiteboard.
Okay. Let me clear.
Can you see it?
Yeah, now we can see it. No, I don't know if on the whiteboard be annotated. I don't think so.
You can't annotate or something?
Wait, I can.
I think you can.
So usually we'll give a drug, or we'll give a drug, it will go like this. Yeah, so this is when you've given a drug, so it's usually concentration against time. So you've given your drug at here, let's say, yeah. So the drug will go up in your blood, and at this peak, this is it's the concentration at which it's maximum in your bloodstream, and then this is your trough. So this is the concentration at which it's lowest in your bloodstream. It's your peak, this is your trough. Then now you'll find perhaps your just another concept that is usually based on this graph is how to dose the medication. You'll find perhaps the therapeutic effect is between this and this concentration. So we want to maintain it at between that concentration being the minimum effective concentration and that concentration being the maximum tolerated dose. So in pharmacokinetics, so if we see that the concentration drops below the minimum effective concentration at around, for example, 6 hours, let's say this is 0 and then this is 6. What we'll want is at 6 hours, this is when we should give the second dose, or about at 5.5 hours, so that it doesn't go to the trough. The point is not for the drug to go to the trough, so that it can again be maintained between this minimum effective concentration and maximum tolerated dose. Yeah. So when immediately it falls below the minimum effective concentration, you should, or just some hours, minutes before that, based on the pharmacokinetic nature of the drug, that is when you want to administer the next dose, so that it's always between the minimum effective and maximum tolerated dose. Nugal, are we okay?
Nice, yeah. Now we get it. Then we also send these photos of the group.
I'm seeing even someone has sent just a photo of the trough. Yeah, I think they'll also send it to the group.
In the chat. I haven't seen that. So answer is D. Guys has explained to us very well. All the following reduce oral availability of a drug except the first metabolism, high water solubility, complexation, reactions with dietary components, esterification of polar parts of a drug molecule. So fast metabolism means the drug is metabolized fast in the it metabolized fast before it reaches most of the parts, yeah. So that will reduce the bioavailability. High water solubility. If a drug is high water soluble and not lipophilic, it's usually that reduces it's more bioavailable if it's lipophilic, right? And then if it's complex with dietary components such as tetracyclics, if they combine with milk or like that, reduces the absorption, right? So esterification of polar parts of a drug molecule, I don't know how that now will affect oral bioavailability.
I think esterification is part of those reactions that drugs undergo.
Doesn't high water
allow the-
solubility increase? Doesn't high water solubility increase oral bioavailability instead of reducing it?
High water solubility. No, if it's high water solubility, that means it's more prone to be excreted, right? That's what I was thinking.
I'm also thinking a bit the same, that if we are having a drug that is highly polar, that is high water solubility, it will barely be able to be absorbed across the lipid bilayer, because it needs to
Yeah.
have some lipidicity to be absorbed.
Yeah, so that means it's more like available for excretion than availability.
Yeah, I think the same too. So
Okay, thanks.
based on that, I'm also thinking choice D, because
But what we were like, let's maybe this increases, but so like if someone understands the meaning of this statement, maybe they can explain to us how this affects bioavailability now, since we have eliminated that answer. You get?
I get. Let me just confirm something before maybe chemistry people. But
Yeah.
my assumption is perhaps my assumption, that is what I'm trying to confirm with the reference, that if a polar group usually undergoes esterification, I'm assuming it will be a bit more lipophilic, this like acetylation, but I'm not sure. I'm not sure. I'm trying to confirm that.
Confirm and let us know.
What I've seen is that the highly hydrophilic drugs find it difficult to cross the lipid layer, so there's low absorption, so unaffected by bioavailability.
Sorry, you said highly?
Highly hydrophilic, those that are highly
Hydrophilic.
hydrophilic, so they find it hard to cross the lipid bilayer, and therefore there will be less absorption. This will reduce bioavailability.
Based on that, there's also now on the esterification part. We know esterification, it just doesn't occur to any polar functional group. It will primarily occur to the carboxylic and to the alcoholic, OH or COH. And based on what I'm finding is that if you esterificate or esterify, I don't know the right term, but essentially, if that carboxylic acid, if that alcohol undergoes esterification, the solubility does decrease, solubility in water. So it makes it a bit more lipophilic when you esterificate those polar functional groups, that is COH and OH. So based on that, I believe that D becomes the opposite of choice B, and D becomes the answer. D for dog.
Oh yeah. To add on that, I was seeing on Google that that esterification is what they use to create now prodrugs. So they're esterified so that once they enter the body now, the drug will be converted into the active form, like like the ester now is hydrolyzed so that it can form the active form. Now that will be more available. The esterification is just to protect it to be more lipophilic so that it's not removed from the body immediately. Is that clear?
Yeah, also I think like when we are dissolving something in water and we're forming these hydrogen bonds, like let's say in any polar molecule, let's say the alcohol part, you have the oxygen and the hydrogen. And both of these atoms now take part in hydrogen bonding with the oxygen also and the hydrogen molecules of water, atoms of water, sorry. But then in the ester, we do not have the hydrogen. So maybe less soluble or more lipophilic. I don't know if I'm making sense though.
Yeah, you are. Anyone else who has something to add on that? Or Shrina, for number 126, it's D. Correct that, please. The ceiling effect of a drug occurs when no clinical response occurs with increased dosage. Proteins involved in active transport are saturated. Renal excretion is overwhelmed. Tolerance occurs. So you guys are saying what is, someone can please explain what ceiling effect is and why we are going with A?
Okay, according to me, I think ceiling is like the high effect. Like they are most effective when, at what point? I think ceiling effect is like, for example, like when we are doing enzymology, we said you can activate like the receptor, like the concentration you have can activate the receptors until a certain point where no matter how much substrate you add, it doesn't have an effect. So the same happens for some drugs. So you can give a drug, and the more you increase the concentration of the drug, the more effect you get. But then it reaches a level and it plateaus. So even when you add more drug, you don't get any effect. So I think now that at that point where you have the plateau, that's the ceiling effect, where no matter the concentration, like even when you increase, you don't get a response.
Okay, that makes sense. Do we have like common drugs that can cause this, like drugs that are very common with this ceiling effect? Drugs that even if you increase the concentration, you don't get more response than what you have. Maybe we can look at that. I'm not sure about painkillers, but I looked, it says that the ceiling effect are more common with drugs that have a dose response curve that plateaus. So example it gave is analgesics, opioid, it specified opioid analgesics. So I'm not sure if painkillers you mean by NSAIDs or by, and then also AC inhibitors. Someone else also gave opioids and benzodiazepines. Okay, drug interactions involve all of the following except enzyme induction, drug complexation, decreased renal secretion, and penetration of the blood-brain barrier. So enzyme induction, we can talk about enzyme, probably if this was not discussed before, we can talk about the enzyme inducers and enzyme inhibitors. So enzyme inducers will is an example of a drug interaction in that it will induce the metabolism of the other drug, hence decreasing its plasma plasma concentration. For drug complexation, that one I don't know if I don't know if that can be explained in simple terms. Decreased renal secretion, yeah, and penetration of the blood-brain barrier. So let's please give our opinions on this question, and also we can summarize enzyme inducers and enzyme inhibitors while we are at it.
I think the drug complexation is describing what we are always saying with tetracyclines, fluoroquinolones, complexing with these ions, such as if you give tetracycline with an antacid. Yeah. So I'd say that is another type of drug interaction. So I agree with Felicia that penetration of the BBB is not it's not a drug interaction.
I have a question. Enzyme induction, is it like the ones that activate the CYP and then they cause others to?
Yeah, like rifampicin.
No. Okay.
And then is induction the one that increases the synthesis and then there's enzyme stimulation, or is it the opposite?
Increases the synthesis of the CYP enzymes.
Yeah.
Yeah,
um,
it's that one.
Okay.
So what are the examples of common examples that you can remember for enzyme inducers?
The one guy has said something. If you it induces the CYPs, so you cannot co-administer with, is it the protease inhibitors or which one? Yeah, something like that. Because it will cause, it will reduce its activity. Or Sami has sent it on the chat.
Okay, there's phenytoin, there's phenobarbital, rifampin, carbamazepine, cryptofulvin, androgens, imipramine, chlorohydrate, polycyclic aromatic hydrocarbon, smoking, coffee, and tea. Okay, that's a nice summary for enzyme inducers. And enzyme inhibitors, those that will inhibit CYP, so they will cause increase in the drug plasma level, causing toxicity.
Somebody can share this screen from here.
Yeah, also have to be somewhere, so someone else has to take through the leading also.
Thank you, everyone. And I'll also not be there at 8, so somebody can take over at 8 too.
So for before the examples, cimetidine, there's cimetidine, omeprazole, antifungals, acetaminophen, SSRIs, cranberry juice, amiodarone, those thyroid hormone, those are the example of CYP450 enzyme inhibitors. Yeah. So I have to go, so someone else to take the leading and also to share the screen.